The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, so today is our third and probably final lecture on approximation algorithms. We're going to take a sort of different approach to proving inapproximability to optimization problems called gap problems. And we'll think about gap-preserving reductions. We will prove along the way optimal lower bound on max 3-SAT and other fun things. So let's start with what a gap problem is. I haven't actually seen a generic definition of this, so this is new terminology, but I think helpful. A gap problem is a way of converting an optimization problem into a decision problem. Now, we already know one way to do that. If you have an NPO optimization problem, you convert it into the obvious decision problem, which is opt at most k for the minimization problem. That is NP complete. But we want to get something useful from an approximability standpoint. And so the idea is, here's a different problem. Instead of just deciding whether opt is at most k, we want to distinguish between opt being at most k versus opt being at least k over c for some value c. And the analogy here is with C approximation algorithm. C does not have to be constant despite the name. Could be a function of n. Maybe it's log n, maybe it's n to the epsilon, whatever. So for a minimization problem, normally, did I get this the right way? Sorry, that should be C times k. For minimization, and for maximization, it's going to be the reverse. And I think I'm going to use strict inequality here also. Okay, so minimization, there's a gap here between k and c times k. We're imagining here c is bigger than 1. So distinguishing between being less than k and being at least c times k leaves a hole. And the point is you are promised that your input... You have a question?
The second one, should it really be c over k?
Sorry, no. Thank you. C and K sound the same, so it's always easy to mix them up. Cool. So the idea is that in both cases, there's a ratio gap here of C. And the idea is that you're promised that your input falls into one of these two categories. What does it mean to distinguish? I mean, I tell you up front, the input either has this property or this property, and I want you to decide which one it is. And we'll call these yes instances and these no instances. Normally with a decision problem, the no instance is that opt is just one bigger or one smaller. Now we have a big gap between the no instances and the yes instances. We're told that that's true. This is called a promise problem. And effectively what that means is if you're trying to come up with an algorithm to solve this decision problem, you don't care what the algorithm does if opt happens to fall in between. The algorithm can do whatever it wants. It can output digits of pi in the middle. As long as when opt is at most k or greater than or equal to k, it outputs yes. And when opt is at least a factor c away from that, it outputs no. Okay, so that's an easier problem. And the cool thing is, if the C gap version of a problem is NP hard, then so is C approximating your original problem. Okay, so this really is in direct analogy to C approximation. And so this lets us think about an NP hardness for a decision problem and prove an inapproximability result. This is nice because in the last 2 lectures we were having to keep track of a lot more in just defining what inapproximability meant and APX hardness and so on. Here it's kind of back to regular NP hardness. Now the techniques are completely different in this world than our older NP hardness proofs, but still it's kind of comforting to be back in decision land. Cool. So because of this implication, in previous lectures we were just worried about proving inapproximability. But today we're going to be thinking about proving that gap problems are NP hard or some other kind of hardness. This is a stronger type of result. So in general, inapproximability is kind of what you care about from the algorithmic standpoint. But gap results saying that, hey, your problem is hard even if you have this huge gap between the yes instances and the no instances. That's also sort of independent interest, more about the structure of the problem. But one implies the other. So this is the stronger type of thing to go for. The practical reason to care about this stuff is that this gap idea lets you get stronger inapproximability results. The factor C you get by thinking about gaps in practice seems to be larger than the gaps you get by L reductions and things. So let me tell you about one other type of gap problem. This is a standard one, a little bit more precise. Consider max SAT. Pick your favorite version of max SAT, or max CSP was the general form where you could have any type of clause. Instead of just a C gap, we will define slightly more precisely an AB gap, which is to distinguish between opt is less than A times the number of clauses, and opt is at least B times the number of clauses. Okay, so whereas here sort of everything was relative to some input k that you want to decide about, here there's, with SAT, there's a kind of absolute notion of what you'd like to achieve, which is that you satisfy everything. All clauses are true. So typically we'll think about B being 1. And so you're distinguishing between a satisfiable instance, where all clauses are satisfied, and something that's very unsatisfiable. There's some usually constant fraction unsatisfiable clauses. Okay, so that lets us be, we need this level of precision thinking about when you're right up against 100% satisfied versus like 1% satisfied or something like that, or 1% satisfiable. Okay.
Do
cool.
we use the same notation for ones there, or only for
Sorry,
the
for
ones
what?
problem, like the maximum number of ones you get?
I haven't seen it, but yeah, it's a good question. Certainly valid to do it for. We will see it for one other type of problem. I mean, for any problem, if you can define some absolute notion of how much you'd like to get, you can always measure relative to that and define this kind of AB gap problem. Cool. All right, so how do we get these gaps? There's maybe 3 ways, I guess. In general, we're going to use reductions, like always. And you could start from no gap and make a gap, or start from a gap of additive 1 and turn it into a big multiplicative gap. That will be gap-producing reductions. You could start with some gap and then make it bigger. That's a gap-amplifying reduction. Or you could just start with a gap and try to preserve it. That would be gap-preserving reductions. In general, once you have some gap, you try to keep it or make it bigger to get stronger hardness for your problem. So the idea with a gap-producing reduction is that you have no assumption about your starting problem. In general reduction, we're going from some problem A to some problem B. And what we would like is that the output instance to problem B, the output of the reduction has, let's say, opt equal to k, or for a minimization problem, opt bigger than c times k. And for a maximization problem, opt less than k over c. So that's just saying we have a gap in the output. We assume nothing about the input instance. That would be a gap-producing reduction. Now, we have seen some of these before, or at least mentioned them. One of them, this is from lecture 3, I think, for Tetris. We proved NP hardness, which was this 3-partition reduction. And the idea is that if you could satisfy that and open this thing, then you could get a zillion points down here. And most of the instances down here, we squeeze this down to like an n to the epsilon. That's still hard. And so n to the 1 minus epsilon of the instances down here. And you're given a ton of pieces to fill in the space, get lots of points. If the answer was no here, then you won't get those points. And so opt is very small. At most, say, n to the epsilon. If you can solve this instance, we have a yes instance in the input, then we get like n points. So the gap there is n to the 1 minus epsilon. So the Tetris reduction, we assumed nothing about the 3-partition instance. It was just yes or no. And we produced an instance that had a gap of n to the 1 minus epsilon. We could set epsilon to any constant we want, bigger than 0. Okay, we also mentioned another such reduction. And in general, for a lot of games and puzzles, you can do this. It's sort of an all or nothing deal. And gap-producing reduction is a way to formalize that. Another problem we talked about last class, I believe, was non-metric TSP. I just give you a complete graph. Every edge has some number on it that's the length of that edge. You want to find a TSP tour of minimum total length. This is really hard to approximate because depending on your model, you can use, let's say, edge weights in, to be really annoying would be 0, 1. And if I'm given a Hamiltonicity instance, wherever there's an edge, I put a weight of 0. Wherever there's not an edge, I put a weight of 1. And then if the input graph was Hamiltonian, it's a yes instance, then the output thing will have a tour of length 0. And if the input was not Hamiltonian, then the output will have weight n. Ratio between n and 0 is infinity. So this is an infinite gap creation, if you allow weights of 0. If you say 0 is cheating, which we did in some papers do, you can instead do 1 and infinity, where infinity is the largest representable number. So that's going to be something like 2 to the n if you allow usual binary encodings of numbers. If you don't, the PB case, then that would be n to some constant. But you get a big gap in any case, right? So you get some gap equals huge. Okay, so these are kind of trivial senses of interapproximability, but hey, that's one way to do it. What we're going to talk about today are other known ways to get gap production that are really cool and more broadly useful. This is useful when you have a sort of all or nothing problem. A lot of the time it's not so clear. There's a constant factor approximation. So some giant gap like this isn't going to be possible. But still, gaps are possible. Now, an important part of the story here is the PCP theorem. So this is not about drugs. This is about another complexity class. And the complexity class is normally written PCP of order log n, comma, order 1. I'm going to simplify this to just PCP as the class. The other notions make sense here, although the parameters don't turn out to matter too much, and it's rather lengthy to write that every time, so I'm just going to write PCP. Let me first tell you what this class is about briefly, and then we'll see why it's directly related to gap problems and where a lot of these gap-producing reductions come from. So PCP stands for probabilistically checkable proof. The checkable proof refers to NP. NP, every yes instance has a checkable proof that the answer is yes. Probabilistically checkable means you can check it even faster with high probability. So normally to check a proof, we take polynomial time in NP. Here we want to achieve like constant time. That's the main idea. That can't be done perfectly, but you can do it correctly with high probability. So in general, a problem in PCP has certificates of polynomial length, just like NP. And we have an algorithm for checking certificates, which is given a certificate, and it's given order log n bits of randomness. That's what this first parameter refers to, is how much randomness the algorithm's given. So we restrict the amount of randomness to a fairly small amount. And it should tell you whether the instance is a yes instance or a no instance, in some sense, if you're given the right certificate. So in particular, if the instance was a yes instance, so this is back to decision problems, right? Just like NP. There's no optimization here. But we're going to apply this to gap problems, and that will relate us to optimization. So let's say there's no error on yes instances, although you could relax that. It won't make a big difference. So if you have a yes instance and you give the right certificate, so this is for some certificate, the algorithm is guaranteed to say yes, so no error there. Where we add some slack is if there's a no instance. Now normally in NP, for a no instance, there is no correct certificate. Now the algorithm will sometimes say yes, even if we give it the wrong certificate. There is no right certificate, but it will say so with some at most constant probability. So let's say the probability that the algorithm says no is at least some constant, presumably less than 1. If it's 1, then that's NP. If it's a half, that would be fine. A tenth, a hundredth, they'll all be the same. Because once you have such an algorithm that achieves some constant probability, you can apply it log 1 over epsilon times. And we reduce the error to epsilon. The probability of error goes to epsilon if we just repeat this log 1 over epsilon times. So in constant time, so it didn't say, the order 1 here refers to the running time of the algorithm. So this is an order 1 time algorithm. So the point is the algorithm's super fast, and still in constant time for constant epsilon, you can get arbitrarily small error probability, say 1 in 100 or 1 in a million, and it's still pretty good, and you're checking your proof super, super fast. Question?
Why is there a limit on the randomness?
This limit on randomness is not strictly necessary. For example, n bits of randomness turn out not to help you. That was proved later. But we're going to use this in a moment. It will help us simulate this algorithm without randomness, basically. Yeah?
If the verifier runs in constant time, can you even read all his randomness?
So this is constant time in a model of computation where you can read log n bits in one step. So your word, let's say, is log n bits long. So you have enough time to read the randomness. Obviously, you don't have time to read the certificate because that has polynomial length. But yeah, constant time. Cool. Other questions? So that is the definition of PCP. Now let me relate it to gap problems. So let's say first claim is that if we look at this gap SAT problem, where b equals 1 and a is some constant, presumably less than 1, then, in fact, that should be less than 1. Why don't I write strictly less than 1 here? This is a constant less than 1. Then I claim that problem is in PCP, that there is a probabilistically checkable proof for this instance, namely, it's a satisfying variable assignment. Again, it's this instance either has the when in the yes instance, all of the entire thing is satisfiable. So just like before, I can have a certificate, just like an NP, satisfying assignment to the variables is good. In the no instance, now I know, let's say, at most half of the things are satisfied if this was 1/2. And so what is my algorithm going to do? In order to get some constant at most constant probability of failure, it's going to choose a random clause and check that it was satisfied. Uniform random. So I've got log n bits. Let's say there are n clauses. So I can choose one of them at random by flipping log n coins. And then check. So that involves, this is 3 SAT, so it only involves 3 variables. I check those 3 variable value assignments in my certificate, just by random access into the certificate. In constant time, I determine whether that clause is satisfied. If the clause is satisfied, algorithm returns yes. Otherwise, return no. Now, if it was a satisfying assignment, the algorithm will always say yes. So that's good. If it was not satisfiable, we know that, let's say, at most half of the clauses are satisfiable, which means in every certificate, the algorithm will say no at least half the time. And half is whatever that constant is. So that means the probability that the algorithm is wrong is less than 1 over the gap, whatever that ratio is. Cool? Yeah.
So does this proof not then hold then for general CNF? So for general CNF,
we will. Let me tell you the PCP theorem is that NP equals PCP. This is proved. So all problems are in PCP, but this is some motivation for where this class came from. Yeah. Okay. I'm not going to prove this theorem. The original proof is super long. Since then, there have been relatively short proofs. I think the shortest proof currently is 2 pages long. I'm still not going to prove it because it's a bit aside the point to some extent. It does use reductions and gap amplification, but it's technical to prove it, let's say. But I will give you some more motivation for why it's true. So, for example, so here's one claim. If order 1, let's change this notation. If less than 1, comma 1, gap 3 SAT is NP hard, then NP equals PCP. So we know that this is true, but before we know that, so we just proved that this thing is in PCP. And if furthermore, this problem, we're going to prove this is NP hard. That's the motivation. If you believe that it's NP hard, then we know all problems in NP can reduce to this thing, and then that thing is in PCP. So that tells us that all problems in NP, you can convert them into less than 1, comma 1 gap 3 SAT, and then get a PCP algorithm for them. So that would be one way to prove the PCP theorem. In fact, the reverse is also true. and this is sort of more directly useful to us, if, let's say, 3-SAT is in PCP, then the gap version of 3-SAT is NP-hard. Okay, this is interesting because this is true because NP equals PCP, in particular 3-SAT is in PCP. And so we're going to be able to conclude by a very short argument that the gap version of 3-SAT is also NP-hard, and this proves constant factor inapproximability of 3-SAT. We will see a tighter constant in a little bit, but this will be our first such bound. And this is a very general kind of algorithm. It's kind of cool. So suppose, so PCP is easy for the gap version of 3-SAT, but suppose there was a probabilistically checkable proof for just straight up 3-SAT when you're not given any gap bound, which is true, it does exist. So we're going to use that algorithm, and we're going to do a gap preserving reduction. So let's say the PCP algorithm we're given, because we're looking at PCP log n comma order 1, runs in constant time. Constant time algorithm can't do very much. In particular, I can write the algorithm as a constant size formula. Okay, it's really a distribution over such formulas defined by the log n random bits. But let's say it's a random variable where for each possible random choice is a constant size formula that evaluates to true or false, corresponding to whether the algorithm says yes or no. We know we can convert algorithms to formulas if they're a short amount of time. So we can make that a CNF formula. Why not? 3CNF if we want. My goal is to, I want to reduce 3-SAT to the gap version of 3-SAT, because 3-SAT we know is NP-hard, so if I can reduce it to the gap version of 3-SAT, I'm happy. Then I know the gap version of 3-SAT is also hard. So here is my reduction. I'm going to, so I'm given the 3-SAT formula, and the algorithm evaluates some formula on it and the certificate. What I'm going to do is try all of the random choices. Because there's only log n bits, there's only polynomially many possible choices for those bits. It's order log n, so it's n to some constant. And I want to take this formula, take the conjunction over all of those choices. If the algorithm always says yes, then this formula will be satisfiable. So in the yes instance case, I get a satisfiable formula. So yes implies satisfiable, 100% satisfiable. That corresponds to this number. I want it to be 100% in the yes case. In the no case, I know that a constant fraction of these random choices give a no, meaning they will not be satisfied. For any choice, any certificate, I know that a constant fraction of these terms, which I'm conjuncting, will evaluate to false because of the definition of PCP. That's what probability algorithm saying no means. So let's say constant fraction of the terms are false. The terms are the things we're conjuncting over, but each term here is a constant size CNF formula. So when I AND those together, I really just get one giant AND of clauses, constant fraction larger than the number of terms. And if a term is false, that means at least one of the clauses is false. And there's only a constant number of clauses in each term. So this means a constant fraction of the clauses in that giant conjunction are also false. And that is essentially it. Let me that is my reduction. So in the yes instance, I get a 100% satisfiable thing. In the no instance, I get some constant strictly less than 1 satisfiable thing, because in any solution, I get a constant fraction that turned out to be false, constant fraction of the clauses. Now, what the constant is, you'd have to work out things. You'd have to know how big your PCP algorithm is. But at least we get a constant lower bound proving, in particular, proving there's no p-task for max 3-SAT. This is what you might call a gap amplifying reduction, in the sense we started with no gap. The instance of 3-SAT was either true or false, and we ended up with something with a significant gap. Fine. So what we're going to talk about next is called gap preserving reductions. But maybe before I get there, what we just showed is that the PCP theorem is equivalent, and in particular we get gap problems being NP-hard. This is why we care about PCPs. Then in general, once we have these kinds of gap hardness results, we convert our, when we're thinking about reductions from A to B, because we know gap implies inapproximability, we could say, okay, 3-SAT is inapproximable, and then do, say, an L reduction from 3-SAT to something else. The something else is therefore inapproximable also. That's all good. But we can also, instead of thinking about the inapproximability and how much carries from A to B, we can think about the gap directly. And this is sort of the main approach in this lecture that I'm trying to demonstrate, is by preserving the gap directly, you get new gap bounds, and generally stronger gap bounds, and then those imply inapproximability results. But the gap bounds are stronger than the inapproximability, and also they tend to give larger constant factors in the inapproximability results. So what do we want out of a gap preserving reduction? Let's say we have an instance x of A. We convert that into an instance x prime of some problem B. We're just going to think about the opt of x versus the opt of x prime. And what we want for, let's say, a minimization problem is two properties. One is that the opt, if the opt of x is at most some k, then the opt of x prime is at most some k prime. And conversely, okay, so in general, opt may not be preserved, but let's say it changes by some prime operation. So in fact, you can think of k and k prime as functions of n. Okay, so if I know that opt of x is at most some function of n, then I get that opt of x prime is at most some other function of n. But there's some known relation between the two. What I care about is this gap c. It should be a c prime here. So this is, what this is saying is, suppose I had a gap if I know that all the solutions are either less than k or more than c times k. I want that to be preserved for some possibly other gap c prime in the new problem. Okay, so this is pretty general, but this is the sort of thing we want to preserve. If we had a gap of c before, we get some gap c prime after. If c prime equals c, this would be a perfectly gap preserving reduction. Maybe we'll lose some constant factor. If c prime is greater than c, this is called gap amplification. And gap amplification is essentially how the PCP theorem is shown by repeatedly growing the gap until it's something reasonable. If you want to say prove that set cover is log n hard, it's a similar thing where you start with a small gap constant factor and then you grow it, and you show you can grow it to log n before you run out of space to write it in your problem, essentially, before your instance gets more than polynomial. Or if you want to prove that clique can't be solved in better than whatever n to the 1 minus epsilon, then a similar trick of gap amplification works. Those amplification arguments are involved, and so I'm not going to show them here. But I will show you an example of a gap-preserving reduction next, unless there are questions. Cool. So I'm going to reduce a problem which we have mentioned before. Which is max exactly 3 XOR and XNOR-SAT. This is linear equations mod 2, where every equation has exactly 3 terms. Right, so something like xi XOR xj XOR xk equals 1 or something. You can also have negations here. Okay, so I have a bunch of equations like that. I'm going to just tell you a gap bound on this problem, and then we're going to reduce it to another problem, namely max E3-SAT. So the claim here is that this problem is 1/2 plus epsilon, 1 minus epsilon, gap hard for any epsilon. Which in particular implies that it is 1/2 minus epsilon inapproximable, unless p equals np. But this is, of course, stronger. It says if you just look at instances where, let's say, 99% of the equations are satisfiable versus when 51% are satisfiable, it's np hard to distinguish between those two. Why 1/2 here? Because there is a 1/2 approximation. I've kind of mentioned the general approach for approximation algorithms for SAT is take a random assignment, variable assignment. And in this case, because these statements are about a parity, if you think of xk as random, it doesn't matter what these two are. 50% probability this will be satisfied. And so you can always satisfy at least half of the clauses, because this randomized algorithm will satisfy half in expectation. Therefore, in at least one instance, it will do so. But if you allow randomized approximation, this is a 1/2 approximation or a 2 approximation, depending on your perspective. So this is really tight. That's good news. And this is proved. This is essentially a form of the PCP theorem. PCP theorem says that there's some algorithm, and you can prove that, in fact, there is an algorithm that looks like this. It's a bunch of linear equations with 3 terms per equation. Okay, so let's take that as given. Now, what I want to show is a reduction from that problem to max E3-SAT. So remember max E3-SAT. You're given CNF where every clause has exactly 3 distinct literals. You want to maximize the number of satisfied things. So this is roughly the problem we were talking about up there. So first thing I'm going to do is, so I want to reduce this to that. And this is the reduction. And the first claim is just that it's an L reduction. So that's something we're familiar with. Let's think about it that way. Then we will think about it in a gap-preserving sense. Okay, so there are 2 types of equations we need to satisfy, the sort of odd case or the even case. again, each of these could be negated, and I'm just going to double negate means unnegated over here. So each equation is going to be replaced with exactly 4 clauses in the E3-SAT instance. And the idea is, well, if I want them all, the parity of them to be odd, it should be the case that at least one of them is true. And if you stare at it long enough, also, when you put 2 bars in there, I don't want exactly 2 of them to be true. That's the parity constraint. If this is true, all 4 of these should be true. That's the first claim. This by the parity of the number of bars. There's either 0 bars or 2 bars, or 3 positive or 1 positive. Those are the 2 cases. And in this situation, where I want the parity to be even number of trues, I have all the even number of trues cases over here. Here 2 of them even, and here none of them even. Okay, and again, if this is satisfied, then all 4 of those are satisfied. Now, if these are not satisfied, by the same argument, you can show that at least one of these is violated, but in fact, just one will be violated. Okay, so for example, so this is just a case analysis. Let's say I set all of these to be 0, and so their XOR is 0, not 1. So if they're all false, then this will not be satisfied, but the other 3 will be. And in general, because we have, for example, xi appearing true and false in different cases, you will satisfy 3 out of 4 when on the right when you don't satisfy on the left. So it's the difference is 3 versus 4. When these are satisfied, you satisfy 4 on the right. When they're unsatisfied, you satisfy 3 on the right. That's all I'm claiming. So so if the equation is satisfied, then we get 4 in the 3-SAT instance. And if it's unsatisfied, we turn out to get exactly 3. Okay, so I want to prove that this is an L reduction. To prove L reduction, we need 2 things. One is that the additive gap, if I solve the 3-SAT instance and convert it back into a corresponding solution to max E3 XOR-SAT, which I don't change anything. The variables are just what they were before. That the additive gap from opt on the right side is at most some constant times the additive gap on the left side, or vice versa. In this case, the gap is exactly preserved because it's 4 versus 3 over here. It's 1 versus 0 over here. So the additive gap remains 1. And that is called beta, I think, in L reduction land. So this was property 2 in the L reduction. So the additive error in this case is exactly preserved. So there's no scale, beta equals 1. If there's some other gap, then if it was 5 versus 3, then we'd have beta equal 2. Okay, then there was the other property, which is you need to show that you don't blow up opt too much. We want the opt on the right-hand side to be at most some constant times opt on the left-hand side. This requires a little bit more care because we need to make sure opt is linear, basically. We did a lot of these arguments last lecture. Because even when you don't satisfy things, you still get points. And the difference between 0 and 3 is big ratio. So we want that to not happen too much. And it doesn't happen too much because we know the left-hand side, opt is at least a half of all the clauses. So it's not like there are very many unsatisfied clauses. At most, half of them are unsatisfied because at least half are satisfiable in the case of opt. So here's the full argument. general opt for the 3-SAT instance is going to be 4 times all the satisfiable things plus 3 times all the unsatisfiable things. This is the same thing as saying you take 3 times the number of equations. Every equation gets 3 points for free. And then if you also satisfy them, you get 1 more point. Okay, so this is an equation on those things, the 2 ops. And we get plus 3 times the number of equations. And because there is a 1/2 approximation, we know that number of equations is at most 2 times opt. Because opt is at least 1/2 the number of equations. And so this thing is overall at most 6 plus 1, 7 times opt E3x nor. Okay, and this is the thing called alpha in L reduction. I wanted to compute these explicitly because I want to see how much inapproximability I get. Because I started with a tight inapproximability bound of 1/2 minus epsilon being impossible, whereas 1/2 is possible. It's tight up to this very tiny arbitrary additive constant. And over here, we're going to lose something. We know from L reductions, if you're inapproximable before, you get inapproximability, in this case of max E3SAT. So what is the factor? If you think of, there's one simplification here relative to what I presented before. A couple lectures ago, we always thought about 1 plus epsilon approximation. And how does epsilon change? And that works really well for minimization problems. For a maximization problem, your approximation factor is an approximation factor of 1 plus epsilon means you are at least this thing times opt. And this thing gets awkward to work with. Equivalently, with a different notion of epsilon, you can just think of a 1 minus epsilon approximation. And how does epsilon change? And in general, for a maximization problem, if you have 1 minus epsilon approximation before the L reduction, then afterwards you will have a 1 minus epsilon over alpha beta. So for maximization, we had 1 plus epsilon, and then we got 1 plus epsilon over alpha beta. With the minuses, it also works out. That's a cleaner way to do maximization. So this was a maximization problem. We had over here, epsilon was different notions of epsilon. Here we have 1/2 inapproximability. That 1/2 is also known as 1 minus 1/2. So epsilon here is 1/2. And alpha was 7. Beta was 1. And so we just divide by 7. So in this case, we get that max E3SAT is 1 minus 1/2 divided by 7, which is 1/14. Technically, there's a minus epsilon here. Sorry, bad overuse of epsilon. This is, again, for any epsilon greater than 0, because we had some epsilon greater than 0 here. Slightly less than 1/2 is impossible. So over here, we get slightly less than 1 minus 1/14 is impossible. This is 13 over 14 minus epsilon, which is OK. It's a bound, but it's not a tight bound. The right answer for max 3SAT is 7/8, because if you take, again, a uniform random assignment, every variable flips a coin, heads or tails, true or false, then 7/8 of the clauses will be satisfied in expectation, because if you look at a clause, if it has exactly 3 terms, and it's an OR of 3 things, you just need at least 1 head to satisfy this thing. So you get a 50% chance to do it in the first time, and then a 1/4 chance to do it in the third time, and general 7/8 chance to get it 1 of the 3 times. 7/8 is smaller than 13/14, so we're not quite there yet. But this reduction will do it if we think about it from the perspective of gap-preserving reductions. So from this general L reduction black box that we only lose an alpha beta factor, yeah, we get this bound. But from a gap perspective, we can do better. The reason we can do better is because gaps are always talking about yes instances where lots of things are satisfied. That means we're most of the time in the case where we have 4s on the right-hand side. Or a situation where we have lots of things unsatisfied. That means we have lots of 3s on the right-hand side. It lets us get a slightly tighter bound. So let's do that. All right. So here is a gap argument about the same reduction. What we're going to claim is that 7/8 minus epsilon gap 3-SAT is NP hard, which implies 7/8 inapproximability, but by looking at it from the gap perspective, we will get this stronger bound versus the 13/14 bound. So the proof is by a gap-preserving reduction, namely that reduction from max E3 XOR-SAT to max 3-SAT, E3-SAT, I should say. And so the idea is the following. Either we have a yes instance or a no instance. If we have a yes instance to the equation problem, then we know that at least 1 minus epsilon of the equations are satisfiable. Okay, so we have 1 minus epsilon. Let's say m is the number of equations. In the no instance case, of course, we know that not too many are satisfied. At most, 1/2 plus epsilon fraction of the equations are satisfiable. So in both cases, I want to see what that converts into. So in the yes instance, we get all 4 of those things being satisfied. So that means we're going to have at least 1 minus epsilon times m times 4 clauses satisfied. We'll also have epsilon m times 3. Those are the unsatisfied. And maybe some of them are actually satisfied, but this is a lower bound on how many clauses we get. Okay. On the other hand, in this situation where not too many are satisfied, that means we get a tighter upper bound. So we have 1/2 plus epsilon times m times 4. And then there's the rest, 1/2 minus epsilon times 3. And maybe some of these are not satisfied, but this is an upper bound on how many clauses are satisfied in the 3-SAT instance versus equations in the 3 XOR-SAT instance. Okay, now I just want to compute these. So everything's times m. And over here we have 4 minus 4 epsilon. Over here we have plus 3 epsilon. So that is 4 minus epsilon times m. And here we have, again, everything is times m. So we have 4 halves, also known as 2, plus 4 epsilon, plus we have 3 halves, minus 3 epsilon. So the epsilons add up to plus epsilon, that much I can see, 4 epsilon minus 3 epsilon. And then we have 4 halves plus 3 halves, also known as 7 halves, yes. Okay, so we had a gap before, and we get this new gap after. When we have a yes instance, we know that there will be at least this many clauses satisfied in the 3-SAT, and there will be at most this many in the no instance. So what we proved is this bound that sorry, get them in the right order. 7/2 is the smaller one. 7/2 plus epsilon, comma, 4 minus epsilon. Gap 3-SAT, E3-SAT is NP-hard because we had NP-hardness of the gap before. We did this gap preserving reduction, which ended up with this new gap, this being for no instances, this being for yes instances. And so if we want to, this is with the comma notation for the yes and no, what fraction is satisfied. If you convert it back into the C gap notation, you just take the ratio between these two things. And ignoring the epsilons, this is like 4 divided by 7/2. So that is 7/8 or 8/7, depending on which way you're looking. So we get also 7/8 gap. Sorry, I guess 8/7, the way I was phrasing it before, is also NP-hard. And so that proves, there's also a minus epsilon. Sorry, I should have kept those slightly different epsilon, but minus 2 epsilon, whatever. And so this gives us the 8/7 is the best approximation factor we can hope for. Yeah?
In the first notation, isn't it the fraction of clauses, so between 0 and 1?
Oh, yeah. 4 is a little funny. Right. I needed to scale, thank you, because the number of clauses in the resulting thing is actually 4m, not m. So everything here needs to be divided by 4. Won't affect the final ratio, but this should really be over 4 and over 4. So also known as 7/8 plus epsilon, comma, 1 minus epsilon. Now it's a little clearer at 7/8. Cool? Yeah.
So are there any CSPs where we can beat randomness?
So for max cut, you can beat the randomness.
Oh, cool.
Randomness would give you 1/2. The Demaine-Williamson algorithm gives you like 1
Good.
something.
So you can beat it by a constant factor. Probably not by more than a constant factor, but yeah. Max cut is an example where you can beat it. I think I have the Demaine-Williamson bound here. Max cut, the best approximation is 0.878, which is better than what you get by random, which is 1/2, I guess. Cool. All right. Cool. So we get optimal bound for max E3-SAT, assuming an optimal bound for E3 XOR-SAT, which is from PCP. Yeah.
So I'm sorry, can you explain to me again why we don't get this from the L reduction, but we do get it from the gap argument, even though the reduction is the same reduction?
It's just it lets us give a tighter argument in this case. By thinking about yes instances and no instances separately, we get one thing. Because this reduction is designed to do different things for yes and no instances. Whereas the L reduction just says generically, if you satisfy these parameters alpha and beta, you get some inapproximability result on the output. But it's conservative. It's a conservative bound. If you just use properties 1 and 2 up here, that's the best you could show. But by essentially reanalyzing property 1, but thinking separately about yes and no instances, this held for all instances. We got a bound of 7.
Right, okay.
But in the yes and the no cases, you can essentially get a slightly tighter constant. Yeah. Cool. All right. I want to tell you about another cool problem. Another gap hardness that you can get out of PCP kind of analysis. By some gap amplification, essentially. Which is called label cover. So this problem takes a little bit of time to define, but the basic point is there are very strong lower bounds on the approximation factor. So So you're given a bipartite graph, no weights. The bipartition is AB. And furthermore, A can be divided into K chunks. And so can B. Again, these are disjoint unions. And let's say size of A is n, size of B is n, and size of each AI is also the same. You don't have to make these assumptions, but you can, so let's make it a little bit cleaner. So in general, A consists of k groups, each of size n over k. B consists of k groups, each of size n over k. So that's our, we have A here with these little groups. We have B, these little groups, and there's some edges between them. In general, your goal is to choose some subset of A, let's call it A prime, and some subset of B, call it B prime. And one other thing I want to talk about is called a super edge. So, and then I'll say what we want out of these subsets that we choose. Imagine contracting each of these groups. There are n over k items here, and there are k different groups. Imagine contracting each group to a single vertex. So this is A1, this is B3. I want to say that there's a super edge from the group A1 to the group B3 because there's at least one edge between them. If I squashed A1 down to a single vertex and B3 down to a single vertex, I would get an edge between them. So a super edge, AIBI, AIBJ, I should say, exists if there's at least one edge in AI cross BJ. At least one edge connecting those groups. And I'm going to call such a super edge covered by A prime, B prime if at least one of those edges is in this chosen set. So if there's at least one edge, if this AI cross BJ, these are all the possible edges between those groups, intersects A prime cross B prime. And in general, I want to cover all the hyperedges if I can. So I would like to have a solution where if there is some edge between A1 and B3, then in the set of vertices I choose, A prime and B prime on the left, they induce at least one edge from A1 to B3, and also from A2 to B3, because there is an edge that I drew here. I want ideally to choose the endpoints of that edge or some other edge that connects those two groups. Yeah.
So you're choosing subsets A prime of A. Is there some restriction on the subset you choose? Why don't you choose like all of A?
Wait.
Oh, okay. You're not done yet?
Nope. That's about half of the definition. It's a lot to say. It's not that complicated of a problem. So there's two versions. It's part of what makes it longer. We'll start with the maximization version, which is called maxrep. So we have two constraints on A prime and B prime. First is that we choose exactly one vertex from each group. So A prime intersect AI equals 1, and B prime intersect BJ equals 1 for all I and j. Okay. And then subject to that constraint, we want to maximize the number of covered super edges. intuition here is that those groups are labels. And there's really one super vertex there, and you want to choose one of those labels to satisfy the instance. So here you're only allowed to choose one label per vertex. You choose one out of each of the groups. Then you'd like to cover as many edges as you can. If there is an edge in the supergraph from AI to BJ, you would like to include an induced edge. Like there should actually be an edge between the label you assign to AI and the label you assign to BJ. So that's this version. The complementary problem is a minimization problem where we switch what is relaxed, what constraint is relaxed, and what constraint must hold. So here we're going to allow multiple labels for each super vertex, multiple vertices to be chosen from each group. Instead, we force that everything is covered. We want to cover every super edge. That exists, and our goal is to minimize the size of these sets. A prime plus B prime. Okay, so this is sort of the dual problem. Here we force one label per vertex, want to maximize the number of covered things. Here we force everything to be covered, want to essentially minimize the number of labels we assign. Okay, so these problems are both very hard. Just to build you some more intuition, let me show you a puzzle, which is basically exactly this game, designed by our MIT professor Dana Mochkovich. So here's a word puzzle. Your goal is to put letters into each of these boxes. This is B, and this is A. And such that, for example, this says animal, which means the three things pointed by the red arrows, those letters should concatenate to form an animal, like cat, bat. All right, that's the example. So if I write B, A, and T, animal is satisfied perfectly. Because all three letters form a word, I get 3 points so far. Okay. Next, let's think about transportation. For example, cab is a 3-letter word that is transportation. Notice there's always 3 over here. This corresponds to some regularity constraint on the bipartite graph. There's always going to be 3 arrows going from left to right for every group. So transportation, fine, we got CAB. That is happy. We happen to reuse the A, so we get 3 more points, total of 6. Furniture, we have B, blank, and T left. This is going to be a little harder. I don't know of any furniture that starts with B and ends with T and is 3 letters long. But if you, for example, write an E here, that's pretty close to the word bed, which is furniture. So in general, of course, each of these words corresponds to a set of English words. That's going to be the groups on the left. So this AI group for furniture is a set of all words that are furniture and 3 letters long. And then for each such choice on the left, for each such choice on the right, you can say, are they compatible by either putting an edge or not? And so this is, we got 2 out of 3 of these edges. These 2 were satisfied, this one's not, so we get 2 more points, so far a total of 8. Okay, this is for the maximization problem. Minimization would be different. Here's a verb where we almost get cry, C-B-Y, so we get 2 more points. Here is another, we want a verb, blank, A-Y. There are multiple such verbs. You can think of them. And on the other hand, we have a food, which is supposed to be blank, E-Y. So a pretty good choice would be P for that top letter. Then you get pay exactly and almost get P. So a total score of 15. And so this would be a solution to max rep of cost 15. It's not the best. And if you stare at this example long enough, you can actually get a perfect solution of score 18, where there are no violations. Basically, in particular, you do say here and get soy for food. So
the sets on the right are 26 letters?
Yes, the BIs here are the alphabet A through Z, and the sets on the left are a set of words. And then you're going to connect 2 of them by an edge if that letter happens to match on the right, the ith letter. So it's a little, I mean, the mapping is slightly complicated, but this is a particular instance of max rep. Okay, so what? Well, we get some super extreme hardness for these problems. So let's start with epsilon comma 1 gap max rep is NP hard. Yeah. So what I mean by this is, in the best situation, you cover all of the super edges. So the 1 means 100% of the super edges are covered. Epsilon means that most an epsilon fraction of them are covered. So that problem is NP hard. This is a bit stronger than what we had before. Before we had a particular constant, comma 1 or 1 minus epsilon or something. Here, for any constant epsilon, this is true. And there's a similar result for min rep. It's just from 1 to 1 over epsilon. So this means there is no constant factor approximation. Max rep is not in APX. Okay, but it's worse than that. We need to assume slightly more. In general, what you can show, if you have some constant p, or there is a constant p, such that if you can solve this gap problem, 1 over p to the k, so a very tiny fraction of things satisfied versus all of the super edges covered, then NP can be solved in n to the order k time. Okay, so we haven't usually used this class. Usually we talk about p, which is the union of all these for constant k. But here, k doesn't have to be a constant. It could be some function of n. And in particular, if p does not equal np, then k constant is not possible. So this result implies this result. But if we let k get bigger than a constant, like log n or something, then we get some separation between, well, we get a somewhat weaker statement here. We know if p does not equal np, we know that np is not contained in p. But if we furthermore assume that np doesn't have sub-exponential solutions and very sub-exponential solutions, then we get various gap bounds and inapproximability on max rep. So a reasonable limit, for example, is that let's say we assume NP is not in n to the poly log n. N to the poly log n is usually called quasi-polynomial. It's almost polynomial. You know, log n is kind of close to constant-ish. This is the same as 2 to the poly log n, n to the poly log n. But it's a little clearer. This is obviously close to polynomial, quite far from exponential, which is 2 to the n, not polylog. So very different from exponential. So almost everyone believes that NP does not admit quasi-polynomial solutions. All problems in NP would have to admit that. 3-SAT, for example, people don't think you can do better than some constant to the n. Then what do we get when we plug in that value of k? That there is a no 1 over 2 to the log to the 1 minus epsilon n approximation. Or also that this same thing, gap is hard. Now it's not NP hard, but it's as hard as this problem. If you believe this is not true, then there will be no polynomial time algorithm to solve this factor gap max rep. So this is very large. We've seen this before in this table of various results. Near the bottom, there was a lower bound of 2 to the log to 1 minus epsilon n. This is not assuming p does not equal np. It's assuming this statement, np does not have quasi-polynomial algorithms. And you see here, friends, max rep and min rep, 2 versions of label cover. So I'm not going to prove these theorems, but again, they're PCP-style arguments with some gap boosting. But I would say most, or a lot of approximation lower bounds in the world today start from max rep or min rep and reduce to the problem using usually some kind of gap preserving reduction. Maybe they lose the gap, but we have such a huge gap to start with that even if you lose gap, you still get pretty good results. So a couple of quick examples here on the slides. Directed Steiner forest. Remember, you have a directed graph and you have a bunch of terminal pairs, and you want to, in particular, connect via directed path some AIs and BJs, let's say. And you want to do so by choosing the fewest vertices in this graph. So what I'm going to do, if I'm given my bipartite graph here for min rep, I'm just going to add, to represent that this is a group, I'm going to add a vertex here, connect by directed edges here, and there's a group down here, so I'm going to have downward edges down there. And whenever there's a super edge from, say, A2, capital A2 to capital B1, then I'm going to say in my directed Steiner forest problem, I want a path from little a2 to little b1. So in general, whenever there's a super edge, I add that constraint. And then any solution to directed Steiner forest will exactly be a solution to min rep. You're just forcing the addition of the AIs and BIs. But it's, again, an L reduction. You're just offsetting by a fixed additive amount, so your gap to opt will be the same. And so you get that this problem is just as hard as min rep. So, yeah. And, well, this is another one from set cover. You can also show node weighted Steiner tree is log n, hard to approximate. That's not from min rep, but threw it in there while we're on the topic of Steiner trees. All right, I want to mention one more thing quickly in my 0 minutes remaining. And that is unique games. So unique games is a special case of, say, max rep or either label cover problem where the edges in AI cross BJ form a matching. Okay, for every choice on the left, there's a unique choice on the right, and vice versa, that matches. Well, there's at most one choice, I guess. And I think that corresponds to these games, right? Once you choose a word over here, there's a unique letter that matches. The reverse is not true. So in this problem, it's more like a star, left to right star. Once you choose this word, it's fixed what you have to choose on the right side. But if you choose a single letter over here, it does not uniquely determine the word over here. So unique games is quite a bit stronger. You choose either side, it forces the other one if you want to cover that edge. Okay? So far, so good. Unique games conjecture is that this special case is also hard. Unique games conjecture is that epsilon 1 minus epsilon gap unique game is NP hard. Of course, there are weaker versions of this conjecture that don't say NP hard, maybe assuming some weaker assumption that there's no polynomial time algorithm. Unlike every other complexity theoretic assumption I have mentioned in this class, this one is a subject of much debate. Not everyone believes that it's true. Some people believe that it's false. Many people believe, or basically people don't know. It's a short answer. There's some somewhat scary evidence that it's not true. There are slightly stronger forms of this that are definitely not true, which I won't get into. There is a sub-exponential algorithm for this problem, but it's still up in the air. A lot of people like to assume that this is true because it makes life a lot more beautiful, especially from an approximability standpoint. So for example, max 2SAT, the best approximation algorithm, is 0.940. If you assume unique games, you can prove a matching lower bound. That was max 2SAT. For max cut, as was mentioned, 0.878 is the best upper bound by Gomez-Williamson. This, if you assume unique games, then that's also tight. There's a matching this minus epsilon, or plus epsilon in approximability result. And vertex cover 2. You probably know how to do 2. If you assume unique games, 2 is the right answer. If you don't assume anything, the best we know how to prove using all of this stuff is 0.857 versus 0.5. So it's nice to assume unique games is true. Very cool result is if you look at over all the different CSP problems that we've seen, all the max CSP problems, and you try to solve it using a particular kind of semi-definite programming. There's an STP relaxation. If you don't know STPs, ignore this sentence. There's an STP relaxation of all CSP problems. You do the sort of obvious thing. And that STP will have an integrality gap. And if you believe unique games conjecture, then that integrality gap equals the approximability factor, 1 for 1. And so in this sense, if you're trying to solve any CSP problem, semi-definite programming is the ultimate tool for all approximation algorithms. Because if there's a gap in the SDP, you can prove an inapproximability result of that minus epsilon. So this is amazingly powerful. The only catch is we don't know whether unique games conjecture is true. And for that reason, I'm not going to spend more time on it. But this gives you a flavor of this side of the field, the gap preservation approximation. Any final questions? Yeah.
If there's a sub-exponential type algorithm, is the unique games conjecture doesn't be NP-hard?
It's fine for a problem to be slightly sub-exponential. It's like 2 to the n to the epsilon or something. So when you do an NP reduction, you can blow things up by a polynomial factor, and so that n to the epsilon becomes n again. So even if you start from 3-SAT, where we don't believe there's a sub-exponential thing, when you reduce to this, you might end up putting it, you lose that polynomial factor, and so it's not a contradiction. Yeah, bit subtle, but cool. See you Thursday.